Um, my name is JC Chiao. I'm a professor at Southern Methodist University. I was the conference censor chair last year. If you missed Dallas, you missed the cowboy dance. I'm presenting for my student, Ms. Chawang. She's preparing for PhD exam, so she couldn't be here. The topic of this talk, presenting for students is always dangerous because she knows everything. I only know a little. So if any tough question, please be kind. We are presenting this as try to find a solution for drifting issue for PS sensor. This work is a collaboration between Southern Methodist University and the University of California at Irvine. First is the motivation that we know there's a lot of pH sensing application, and what we are targeting are electronic diaper, bandage, or food monitoring. This kind of pH sensing has two requirements. One is that it has to be flexible substrate so that they can attach to tissue. And the second thing is it has to be low loss, so we can use a smartphone to power up the sensor and return with the information. There's a lot of measurements need to be done. So long-term measurement is a requirement, but so-called long-term is a few days or several weeks. Nobody going to wear a diaper for several weeks, of course. There's a drifting problem for flexible pH sensor. And this drifting problem usually is a long tail. They take a long time for pH value to settle. So if this happens, there are two issues. One is that you need to calibrate the sensor frequently, or you need to try to find a way that when do I take the data? So the slow response time is a major issue that changed the sensitivity. So we have been developing two different types of iridium oxide sensor. They are material efficient. That means that whatever material we use are on the sensor. So it's unlike a sputtering or e-beam evaporation, you waste a lot of material. Iridium oxide has a wide pH sensing range, and it doesn't interact with our skin or tissue. And we can also make the sensor on flexible substrate so they can conform on the tissue, and we can make it very small. So we use two different type of fabrication technique. And one is that we prepare the iridium powder in a precursor solution, and then we make a paint, and then we use a printing process, like a printing newspaper on the flexible substrate. This is what we call sol-gel process. After that, the printed substrate then is baked in the oven to convert to iridium oxide. The other way is the traditional way that if there's a conductive metal on the flexible substrate, we can use electroplating method at the room temperature, and it will grow the iridium oxide directly on the film. One of the approach is anhydrous iridium oxide, because the baking take away most of the water molecule. And the other one, electroplated, is hydrous oxide, because there are a lot of water molecule trapped inside the iridium oxide. So we do expect that there will be different response to the drifting mechanism. What we try to do is that if a pH sensor has a long drifting curve, usually it happens is that when you put the sensor into the solution, you have a spike. And then gradually the potential comes down. So when do you measure the potential is very difficult to tell. So what we want to do is convert it into something, and I will talk about that later, that make the drift, make the potential settle very quickly, so we know when to take the measurement result. So what we did is that we use something called chronoamperometry. Is that in that technique, you apply a potential voltage and you observe the current change with time. We found out that the current can settle very quickly. So we are thinking that, can I apply a DC bias to the sensor to modify the oxide surface in order to make the surface like the original one. So I can take the data every time like this is a fresh sensor. So we want to use this to quickly settle the potential so we can get a better response time. So what we did first is that we put the sensor into a pH 7 PBS solution. PBS solution has enough salt that mimic the body fluidics. And then we test the sol-gel and the electroplated, and we put different potential, and we observe how the potential drift. We found out for sol-gel, if we apply 0.2 to 0.35 volts, the potential basically stays flat. Versus electroplated, we apply minus 0.1 volts to 0.3 volts, and the potential drift are minimized. So we decide, okay, these are the voltage range. We should do the potential reset. So give you a typical example here, and then I will skip the rest of them. For a sol-gel, we started with a fresh electrode, and we found out the drift is about 20 millivolts. And then after 2 hours, we set a reset voltage, 0.2 volts, and we found out that now the drift become worse, become 29.7 millivolts. And then after 2 hours, we reset again, 0.35 volts, and now we found the potential change again. And then in the end, we reset at 0.3 volts, we found the potential drift is minimized. So we know that, okay, for sol-gel in acid, we should probably use 0.3 as a reset voltage. So we repeat the same thing for electroplated. We found out the best reset is minus 0.1 volt. All the others, either the best one is a 0 volt, that is only 2.6 millivolts drift. All the others either make it worse or not as good. We do find out that these phenomena are different in acids versus alkaline. For alkaline, for the sol-gel process, we found that 0.28 volts gives the best drift performance. And then when we tried this for electroplated as expected, because one is anhydrous and one is hydrous, the performance was completely different, but yet we found 0.275 volts probably is the best drift performance. So then we decided, okay, maybe for acid, we should have 0.3 volts reset, and for alkaline, we should have 0.28 reset. And then we start our experiments. For sol-gel and electroplated, we use freshly prepared electrode. That means they have not touched any solution. And we prepare 3 electrodes so we can observe the uniformity of the device, 3 for acid and 3 for alkaline. First, they got tested, and you can see there's a drift problem for all 6 of them. However, then we applied reset at 0.3 volts for acid and 0.28 for alkaline. We found the potential settle very quickly. Within 2 seconds, they are flat. And for electroplated one, the phenomena is also the same that we found originally they had drift, and when we apply a voltage, after 2 hours, the drift disappeared. We also find something very interesting, that after 4 hours experiment, we wash them, dry them, put them away. After 14 days, we test them again. For the sol-gel one, you can see that in the beginning, even we didn't reset the voltage, the potential was very similar to previous, except the alkaline has a little bit drift problem. But after 2 hours, we reset them again, then the potential becomes flat again. For electroplated, after 14 days, however, the drift become the same or worse. We believe that this is the hydrous water molecule is doing its work. However, even it has drift, after 2 hours, we reset the voltage and it becomes flat again. So we believe that the reset bias and now can improve the drift issue. But how does that do for the sensitivity and hysteresis? So for Sogeo electrode, we do the stepwise measurement. We reset, and then we do 1 cycle and 2 cycle. 1 cycle from 2 to 7, 7 back to 2. And the other one is alkaline from 12 to 7 and back to 12. This is 1 cycle, and this is the second cycle. We found out that the Sogeo device 1 to 3 was very uniform. However, device 4, one of the device has a slightly different performance. We did find out that the device 4 has a slightly difference is because when we printed, the device 4 is on the edge. So maybe the thickness was different from 5 and 6. So using this measurement, we can see that the response are pretty repeatable after the reset. Then we take the result and plot the sensitivity curve. We plot it for cycle 1, and cycle 2. The cycle 1, the device are still being hydrated. So we do expect that the performance is a little bit less than the hydrated one. But we found out that the sensitivity in acid and alkaline are pretty much the same. And when they approach from acid or alkaline, the performance at 7 is roughly the same. However, we do see a little bit difference there, and we counted that as a hysteresis. So doing that, we collect the hysteresis information. The blue one and the black one is the cycle 1, red one and the green one are cycle 2. Then we do found out that in the first cycle, even pH 7, it has a huge hysteresis. That means that when you compare 7 to 7, there's a difference of the potential. But after the second cycle, all this hysteresis disappear. So again, we believe that the drifting issue also solved the hysteresis issue. So this is for Sogeo. For electroplated, because electroplated are uniform when we do all 6 devices. So the 6 devices, the performance are roughly the same. Again, we do cycle 1 from 2 to 7, 7 to 2, that's the first cycle. 2 to 7, 7 to 2, that's second cycle. And for alkaline is 12 to 7, 7 to 12. And we do find out that the performance are repeatable after the reset. However, when we compare the sensitivity, we found something very interesting, is that although the slope are roughly the same, when one device go from acid, one device from alkaline, they do not meet in the middle. For 7, these 2 devices perform differently. We believe that is because when the cycle started with acid, is changing the oxide surface, oxide state on the electrode. And when they go from alkaline back to 7, the hydroxide is changing the surface. And therefore that when they meet at 7, they have a potential jump. This means that if we use electroplated electrode for pH sensing, we do need to calibrate towards 7 to make sure that the 7 will give you the same potential. And for this, that electroplated one, we did find out the slope is higher than the Sogeo one, which means electroplated sensor has a better sensitivity. And this is the result for hysteresis. Again, blue and black are the first cycle, and the red and green are the second cycle. Again, it shows that at the second cycle, the hysteresis almost disappeared. That means the drift problem did fix the hysteresis issue. So to compare electroplated with Sogeo, these are 2 main takeaway points. For Sogeo, the sensitivity between acid and alkaline are roughly the same. And for electroplated one, the sensitivity is better than the Sogeo electrode. However, You can just see the bar here. You can understand that the hysteresis is worse for the electroplated one. And we do believe that that's because the surface state got modified in the solution. So to conclude my talk, we do find out that by externally apply 2 minutes reset bias, you can improve the pH sensor and improve the phenomena of potential drifting. And this potential drifting issue, once it's fixed, we can make sure that all the pH response in batch production will be the same, and it also reduce the hysteresis. And this guarantee that we can use the sensor for long-term measurement without calibration. Also, we test 2 different types of film, hydrous versus anhydrous. We found out hydrous sensor has better sensitivity, but anhydrous sensor has lower hysteresis. And however, the reset bias improved both films, so which means that we can use this reset bias approach for all the pH sensor in the same application. We also find out that anhydrous film that still have a long-lasting reset effect even after 14 days without using the electrode. And the hydrous one, we found there's a surface modification at pH 7, so which means that you do need to calibrate toward pH 7. So this opened a new possibility for us to use this flexible, low-cost pH sensor for biomedical application without frequent calibration. So that concludes my talk, and this work is sponsored by Templeton Chair Endowment. Thanks.